We will begin only 1 minute behind schedule. So welcome everyone. Today we are going to have Uwe Nagel from the University of Kentucky. And he's going to tell us about graded Betti numbers of Jacobian ideals of hyperplane arrangements.
Yes, so thank you very much for the introduction. Thanks for giving me the opportunity to talk. And I realized I failed to write my title, so let me just write Jacobian ideas as an abbreviation. And this is an ongoing joint work with Froh and Migliore. Well, about hyperplane arrangements, and hyperplane arrangements are pretty easy to define. So, and generally they'll look for hyperplane arrangements in projective space. And I will always abbreviate this, or denote this by A, and that's the projective space, and that's just a union of, let's call it a finite number, let's call this number D, disjoint hyperplanes. So, formally, A is a union of hyperplanes HI, and they are just to fix notation. Projective space will always be projective space over a field, and where we assume the field is algebraically closed and the characteristic is 0. That will be convenient. And then, well, each hyperplane is just, well, the vanishing locus of a linear form. So this is all the points in projective space that vanish on this linear form 0. And so Li is an element of degree 1 in the polynomial S1, polynomial S, and so we denote the variables by x0 up to xn, and use always standard grading. That's just a pretty standard notation. And so that is a hyperplane arrangement. And so maybe one thing to note, I mean, you know A, and I will denote this also by A sub F, it's just given by the product. This is just a polynomial of degree D, which is a product of D linear forms. And the point is, well, I mean, we assumed disjoint, not disjoint. Distinct, yes, very good, thank you. So distinct, disjoint, that would be pretty impossible, except if, well, if n is 1, but I mean, that we don't care. So this is a square-free polynomial. All right, so, I mean, hyperplane arrangements have been studied from many points of view. In topology, topologists typically look at the complement and want to understand the cohomology of the complement. Combinatorists often are interested in counting, for example, the number of chambers in the complement. But we'll look at these from an algebraic point of view. After all, this is a special semester on commutative algebra. So we'll be talking about algebraic properties. And there is a class of hyperplane arrangements with very particular and favorable properties. And to introduce these, let me call what's the Jacobian idea of A or AF. That's just, well, we will just denote this by Jack F, and this is just the idea generated by the partial derivatives of f with respect to the variables, like 0 up to xn. And then, so maybe a few comments. The first, well, the polynomial f is in its Jacobian ideal, and that's just because of the Euler relation. D times f is the sum over xi times the partial with respect to xi. Right, and this is where characteristic 0 is really helpful. Otherwise, this would not necessarily be true. Second, the Jacobian, this defines the singular locus set theoretically. So of the hypersurface defined by f. And so then so therefore it's clear, I mean, if two hyperplanes meet in a point, that will be a singular point. That shows, well, the codimension of this Jacobian ideal is always 2. All right. So that's what we always have. And now we want to look at syzygies of the Jacobian ideal. So, okay, so, well, by definition, the Jacobian ideal is generated by partial derivatives. F have degree d, derivatives have degree d minus 1, and they be n plus 1 generators. So there's certainly a surjection, let's call it phi, where we have n plus 1 copies of f of the polynomial ring shifted by minus d plus 1. And that is I mean, I made this degree shift to make this a homogeneous map of degree 0. And then the kernel is the syzygy module. And now we say that the arrangement defined by f, so A, the arrangement is called free if the kernel of phi is a free S module. And of course, I wrote it in this way because then justifies the name. But of course, algebraically, that just means the Jacobian ideal is Macaulay, right? Or more properly, I should say, call it a perfect ideal, but let me go with Macaulay. Right? Okay, so basically, free arrangements have the shortest resolution possible, so that indicates perhaps maybe they should be quite special and have good properties. But to get a feeling for it, let's look at some examples. So, and let me choose just n equals 2, so we're on the projective plane. And then for the first case, we just use the free coordinate lines. So in this case, so f is just the product of the variables x0, x1, and x2. And then, well, that's easily computed. What's then the Jacobian ideal? Well, that's just the intersection of free prime ideals x0 defined by x0, x1, x0, x2, and x1, x2. And so this is the ideal defining the free coordinate points. Well, that is certainly call Macaulay, so this arrangement is free. Now, let's add to this one line. So let's add a line. And now let's take f times the sum of the variables. And well, now I don't want to write down the complete primary decomposition, but let me just say it's an ideal I and another a primary ideal Q where I defines, well, okay, so now we have 4 hyperplanes. Any 2 of these meet in a point, so it gives us 6 points. And these are singularities, so the ideal of the 4 choose 2 points. And this Q has higher codimension, so I can indicate this, that the radical of this is just the irrelevant maximal ideal. So that shows, well, the Jacobian ideal is not unmixed. Components of codimension 2 and codimension 3. So then now, if I call this F times L, so if I add this line, this is not a free arrangement. All right, questions?
Are you getting like star configuration, the ideal on?
Yes, that is one. Yeah. Yes, this is.
Scale up then? Like,
Yeah, so if you take so if you take all, I mean, yeah, if you in your n space and take the n plus 1 coordinate planes and this non-order form, the sum of the variables, for example, yeah, you get a star configuration. I mean, for only for those who know what a star configuration is. Otherwise, it doesn't matter. But yeah. All right. Now, so here we had a nice free arrangement, adding 1 hyperplane, destroyed this, and but there is a famous conjecture by Terrao, and he proposed this conjecture in 1980, and that is typically stated as freeness is a combinatorial property. So what does it mean? More precisely, it means it should only it depends only on the intersection lattice. What's the intersection lattice? You just record how do the hyperplanes meet? Number of codimension 2 intersections, codimension 3 intersections, and so on. So it depends only on the intersection lattice of A. So in other words, if you have 2 arrangements with the same intersection lattice, one is free, the other one is free as well, and otherwise, I mean, yeah. In this sense, this should be combinatorially determined. Now, by now, actually, conjecture is pretty old. So, which indicates it may not be such an easy question. And so, before we wondered, well, maybe one should modify the question a little bit. And so let me introduce what we want to consider, let me recall some definitions, and that's still okay. So let me define. So now let's take, and these definitions one can do for any homogeneous idea. Well, actually any idea, but let's say this is a homogeneous idea. And then we want to find the top dimensional part. And that we just denote by I superscript top of I. That's just the intersection of components, primary components of minimal codimension. So equal to the codimension of I. And then maybe better known is what's called the saturation. Which we write I superscript sat, and that is just well, here we throw away anything of larger codimension. Here we throw only away anything of codimension n+1, which I could formally write as the union of colon ideals m to the k. K is at least 1, and where m is the maximal ideal generated by the variables, right? And then so that, and now we want to apply this to our Jacobian ideal. And so what is clear from the definitions, the Jacobian ideal is contained in its saturation, and this is contained in the top dimensional part. In general, all these inclusions are strict, but if you're on the projective plane, these two agree, right? Then there is only codimension possible greater than 2, and that we throw away. So if we come back to our example, over there, or maybe let me write continued. So where are in the second case where we had F times L, we have seen that the saturation of this is really just this idea I given the 6 coordinate points, and that is what is Corey. Whereas of course, the original Jacobian ideal was not Corey. And so what the questions are when I proposed are the following. So the first is ambitiously asking, when is the Jacobian or the top dimensional part Corey? And of course, this is Terraro's question. I won't look at this one, but this will be the focus, what I'm interested in. And similarly, well, Terraro's conjecture is all about combinatorial, but freeness is a combinatorial property, so let me state it vaguely. When are properties of the top dimensional part, again, I could write the original Jacobian as well, but the focus of this, when are these combinatorially determined? And of course, I haven't said which properties, but part of the question, figuring out which ones are. Yes.
Do any of these questions make sense if you take an irreducible form of degree D? I mean, you're assuming F is product of linear form, right?
Yeah. Oh, well, I mean, well, if you have just one, yeah, you could ask these questions, but first of all, you would have to, I mean, yeah, it is interesting. Well, it is interesting, but let's see. First of all, you want to consider singular hypersurfaces, and then it depends a lot on the singularities. And understanding the singularity of one hypersurface is already not so easy. And if you're interested in arrangements, you typically want more than one at least. And if you allow arbitrary complicated hypersurfaces, you have to account for these singularities as well. So, but yeah, in general, you could ask all these questions also for an arbitrary polynomial. Maybe let's say square free to avoid some trivialities. And it is, I mean, then you would speak of a hypersurface arrangement, and before, and we have also looked at hypersurface arrangement with regards to this question, not so much with regards to this one. Okay, but today I will stick just to hyperplanes because I know these are smooth and so and nice and easy. Well, at least an individual one. Okay, so let's look at one example. And so I will give it a name. We're talking about one pencil. So let's look for fixed D-linear forms in the ideal of generated by two other linear forms. These will all be linear forms. And then, so these are two linear forms, so they define a codimension 2 subspace, and these define hyperplanes containing this codimension 2 subspace. So the cartoon, if n is 2, this would mean, I call this the ideal of P. It would define we have a point P, and then we have a bunch of hyperplanes passing through this point. And then if you look for, and therefore I call this a pencil, even though the picture works in any dimension. And then if you take the Jacobian of this product, this is what I call a complete intersection. Because if I call this F, the Jacobian of S is just given by two partial derivatives, namely I differentiate with respect to the generators of this ideal. Right, so in particular, this is a complete intersection, beautifully Macaulay, this is a free arrangement. The easiest one could write down. And well, I mean, of course, right? I mean, I have just one point, one special point, and only the number of hyperplanes matters to describe the whole Jacobian idea, perfectly combinatorially defined. To go on, we want to have a notation that describes the support of the singular locus. So let me define S of A. This is the set of codimension 2 subspaces defined by taking two distinct hyperplanes in A. Well, I boxed myself. So these are, I mean, these are all describes all the singular points, and then it's clear that this defines the support. So the radical of the Jacobian is just the ideal defining this support. Okay, now, so this gives us this describes the radical, and but there's one well-known and very useful and foundational result which actually describes more of the primary decomposition of the Jacobian. And let me maybe I should do it this way. Let me state it this way. So this describes the primary decomposition of the top dimensional part of the Jacobian as follows. So we take the intersection over all codimension 2 subspaces in the set support S of A, and then we take the Jacobian of a polynomial G that depends on this codimension 2 subspace. And what is G of P? So this is the product of linear divisors of F in the ideal of P. So just as with an example, right here, this would be the ideal of P, and we have a product of linear forms. And as we have seen, these Jacobians are always all complete intersections. So each of these primary components is a complete intersection. And as I said, this was a well-known, seemed a well-known result, but Juan and I couldn't find the proof in the literature, so we made sure it's actually correct. And yes, it is. And actually useful. And okay, so one consequence of this is now this Jacobian will be a radical ideal, well, if and only if it's to the ideal equal to the ideal of a point. That can only be if this has degree 2. So there are only 2 hyperplanes meeting, not more, right? So the radical of the ideal of the Jacobian of P is the ideal of the point if and only if the degree of this polynomial is 2. Exactly 2 points meet. All right. Okay. Everybody good? So then let's yeah, they all cover dimension 2. Well, it's all the top dimensional part. Yeah, so it's an intersection of codimension 2 complete intersections. And in the sense we know, I mean, even what they are, right? I mean, this is explicitly given here, and there I told you what the Jacobian is. All right, now I want to state a condition where we know answers to my questions. And this is a result which I will dub disconnected cycles, tensors, sorry. So to do this, let me define what should be as 0 of A. We should be all the codimension 2 subspaces in the support where the degree of the polynomial is at least G sub P is at least 3. So all the codimension 2 subspaces where at least 3 hyperplanes intersect. And then the first part was with Korn and also Schenk in 2021, when the Jacobian is actually always called Macaulay. No, but we need an assumption. We haven't really assumed anything. That would be too much. Because that we have seen is wrong. So I need to state an assumption. Oh, I guess I will erase it. Let's see. So let's assume. Sorry. Assume no hyperplane of A contains 2 distinct elements of a 0 of A. This is what we need, and then we can actually prove that in this case, the top dimensional part of the Jacobian is always called Macaulay. And then recently, we showed we can actually also compute the graded Betti numbers of this top dimensional part. And so let T be the cardinality of the set as 0 of A, and S the number of hyperplanes it's up. Oh, I started the wrong way. Not containing any center of a pencil in S0 of A. And in this case, when the minimal free resolution of the Jacobian, the top dimensional part looks as follows. Oh, and I better copy this. So let's, yeah. So we have the top dimensional part, and then, so we have generated, it still has only generators in degree d minus 1, but the number is s plus 2t, where s and t are defined, then where are s plus t minus 1 linear syzygies and further syzygies, and this is where for each codimension 2 subspace in a 0 of A makes a contribution. Namely, we have to shift by, so the syzygy has degree D plus the degree of this polynomial G of G sub P minus 2, so here I have to have a plus 2. So that Yes.
Do you have
Ah. No, not perhaps later, but not yet. And yeah, I mean, I said not yet because I mean, so this result, I mean, this result Born and I generalized for hypersurface arrangements, but we haven't thought about extending this result. But good question. Yeah, we could ask all these questions in greater generality, and they make sense. Okay, so this is as you see, I mean the graded Betti numbers are completely combinatorially defined, right? We just need S and T, and of course one assumption to make this work. So maybe let me write down one example, and just so let's maybe have say two disconnected pencils. So we have two disconnected pencils. So S is 2, but let's assume T equals 0. So what's the cartoon? If N is 2, the cartoon is simply, well, we have two pencils. Now I need another one. So these are centers of the pencils P1 and P2. And then, so I have, let's say this is, these are, for each point, we have in each of these points, well, centers of the pencil, we have three hyperplanes meet, and so we have D is 6, we have 6 hyperplanes, and so our resolution in this case is the top dimensional part. We have 4 generators of degree 5 and 1 linear syzygy and 2 syzygies of degree 7. So given by quadrics. All right. So that we know. But now let's tweak this. Now we add a line to P1 and P2. So if you do this, I should have made the picture a little bigger, but anyway. So then we would get this arrangement. And that does not meet the assumption of our theorem. So this is not enough, the theorem is not enough to describe what is going on. And so to understand this arrangement and more complicated arrangements, a new idea is needed. And well, you know something about Juan and me, we like liaison theory, so we want to link. And so let's do this. So let's make a following definition. We choose a linear form, general. And then we want to define what I call the general, and often I will drop general residual of a hyperplane arrangement given by F. I will denote by R sub A. And that is just, well, the residual from linking. So I take a complete intersection generated by F, and then I differentiate with respect to the chosen general linear form. And then I take the colon ideal with respect to F. And now, I don't know, maybe I should. So in general, what is the colon ideal? Maybe I should recall this, right? These are all the polynomials H in S such that H times B is in A. And so that's the colon ideal. And okay, so yes. Well, in a sense, in calculus, you would call it directional derivative, or you think of this as a differential operator, how you would differentiate with respect to a polynomial. Yeah. Yeah. Yeah, please ask. Okay, now let's make two notes. Well, first, well, obviously, the residual depends on the choice of this linear form L. But we assumed it's general. So for example, the gradient Betti numbers of the residual do not depend on the choice of L. And the second, by standard facts in liaison theory, the top dimensional part of the Jacobian ideal is called Macaulay if and only if this residual is called Macaulay. So if you want to understand then this is true, it's enough to look here. And that's our strategy. So we want to look at the residual. Well, to get started, let me describe the primary decomposition of this residual. And this is simply stated as follows, namely, well, I can describe it explicitly, but I have to tell you how to get particular linear forms out of my arrangement and L. So let's write for the linear form, assume it has coefficients AI, and then let's write L dual for the point in projective space whose coordinates are the coefficient of the linear form. So this is just a point dual to our linear form L. And now, for any dimension 2 subspace in our set S of A, fix L sub P in this is a linear form. And what should it do? That should define the hyperplane, which is spanned by P, codimension 2, and the dual point. So this is spanned by P and the dual point, right? This is unique. You have a you have a codimension 2 subspace, 1 point outside, because This was chosen general. This is a general point that determines the hyperplane. And then the primary decomposition of our general residual is again, well, supported on the set S of A. And now the ideals, well, one generator is a linear form, the one I defined here. And then there's one more generator, but I don't give it to you explicitly. Let me just write, I take the ideal of P to the power G of P minus 1, the degree of G of P minus 1. But in fact, this is a complete section. And the generators have degree 1 and, well, one more, right? The degree of G of P minus 1. So the number of hyperplanes meeting in P, because it's an S of A, there are at least 2. So this is at least 1, but it could be more, depending how many hyperplanes pass through P. That's the primary decomposition. If you compare, well, it's similar to what we had for the top dimensional part, except the ideas are in fact even simpler, right? Now here we have 2 generators of degree, well, G of P minus 1. Here we have 1 of this and a linear form. Okay, but as a corollary, we get again the radical of the general residual is the ideal defined by S of A. Okay. Any questions? Let's see. So now, okay. These ideas, these general residuals have actually quite a particular structure, right? They're sort of rather explicitly defined, and their properties also seem quite particular. And as one indication, let me state the following result. For those of you who know what's the Casanova-Mumford regularity, this is exactly always D minus 1. So the number of hyperplanes minus 1. And O of A has always at least one minimal generator of degree E minus 1. So there is a minimal generator of degree minus 1, which shows the regularity has to be at least D minus 1, but it's actually equal on the nose. All right. Now, one consequence of this is the following. So if the Jacobian of F is Macaulay, which is equivalent to saying that the residual is Macaulay, then the graded Betti numbers of the top dimensional part of the Jacobian determine those of the general residual, and well, the converse is true as well. So if we know something is called Macaulay and we ask about the graded Betti numbers, we may again as well study the general residual. And this has allowed us to compute graded Betti numbers in this situation and more general, but I'm afraid I'm out of time. So I will just say it this way. I want to add one more result, at least just state the result orally. We have more special results or more results in the projective plane. So if n is 2. In this case, we had seen the top dimensional part is the same as the saturation. And what we can show if you know the graded Betti numbers of the saturation of the Jacobian ideal, they determine the graded Betti numbers of the original Jacobian ideal, completely and explicitly. So in this case, if you know the Betti numbers of the top dimensional part, we know the whole Betti numbers of the Jacobian ideal in particular. And again, we can, so this is, I mean, if n is 2, this would be also a situation where we could write down the graded Betti numbers of the original Jacobian and more complicated situations. But it's a little tricky to formalize this, so I won't state this, but I just wanted to announce this and say, hopefully, I convinced you that there are interesting questions about Jacobian ideals and their relatives, and more research should be done, in my opinion. Thank you for your attention.
Awesome. Are there any questions?
Anna?
I think it's okay at this point.
Okay, yeah. You have conditions when the top degree is equal to saturation, or is it kind of very mysterious?
Oh, yeah, I mean, this is, so when the top degree is equal to the, that's a good question. I mean, well, if n is true, it's always true. Otherwise, this is actually pretty challenging. No, I don't. No, I don't have a good. I wish I had a good answer for this, but I don't. I mean, this is.
Future problem.
Yeah. Well, this is one of the questions which definitely I would like to understand better. Yeah.
I have a question, which is, I'm having a little bit of trouble understanding. So you had said that like L was general.
Yeah.
So how does the line? I might be misunderstanding the connection because the line that you drew in red here
has nothing to do with this.
It has nothing to do with
no. This is just this So this is just a general linear form which I just need to define with residual.
Okay.
Has nothing. I mean, it
has nothing to do with the extra L that you're adding.
Yeah, it has nothing to do with the hyperplane arrangement. And in fact, I mean, you should imagine you have chosen your hyperplane arrangement. Afterward, you choose this general linear form to determine the general residual. And so if you have more than one hyperplane, I would have think of it, well, I had chosen the lines in white, and then I have chosen the red line. And for both, I used the general linear form to determine the general residual.
Great.
Thanks for asking. Yeah. Great.
You mentioned towards the end now that Betti numbers of the saturation. So I was wondering if that's something that could be abstracted a little bit and say there's some conditions that give you that, or is it very specific to different fields?
Oh, that. I. That's a good question. Let's see. Hey. Let me say it this way. There are bits and pieces of the argument which could be, which are true in greater generality. The whole thing, maybe a little bit, but I'm not so sure. Yeah, so some of the parts I think work in greater generality, but it comes together in a very nice place. Yeah.
Okay, are there any other questions or questions on Zoom? Seeing none, let's thank Uwe again.